Let's walk through a specific example. And I know this is going to sound a little silly, but the example that we're going to be working with is the punting ability of NFL punters and the predictors that we have on the length of their punts is the physical characteristics. Now, each volunteer punted a ball 10 times, so we have 10 observations for 13 players, so we have 130 observations. And again, the outcome that we're interested in is the distance that the football traveled for each of the kicks. The predictors that we have for the distance are hang time in seconds. We have right leg strength in pounds, so they must have been doing some either leg lifting or maybe some pressure outputs from the punts themselves. But we also have the same information for left leg strength as well. Now, we also have the degree of flexibility in both of their legs as our final predictors. And as many of you can guess, that some of these are going to be highly correlated with each other, right? Like a certain amount of hang time is going to be correlated with distance, but your ability to get that hang time is going to be correlated with your leg strength. And it may not necessarily be the case that you need both of your legs to be strong and flexible to kick far, but I can't imagine that it would hurt. And if we added in overall strength, then we could certainly imagine that many of these predictors are highly correlated. Now, to begin, remember, let's just take a look at the bivariate correlations and scatter plots of all of our predictors and outcome. And like I said, we can definitely see that many of these are highly correlated with each other, right? So hang time is clearly highly correlated with both right leg and left leg strength, as well as overall strength. Maybe right leg flexibility, left leg flexibility does seem to be positively correlated, but not necessarily so. So you can see really quickly that many of these covariates vary together and that it may be difficult for us to estimate the partial effect of which variable is doing the most work in helping us explain variation in our outcome. This becomes even more immediately apparent if we look at the correlation matrix between our outcome and all of our covariates. So again, we can see that hang time is incredibly highly correlated with all of our measures of strength and flexibility. If we were to begin to think about what variables we'd include in a regression model, we need to think about the linear relationship of the predictors on each other as well as the outcome. And really, they all seem to have a linear relationship with each other, maybe with the exception of left flexibility. And this one just seems to have some outliers, and it does have the lowest correlation with all the other variables, but really, again, it was at almost 0.6, so that's still a quite high correlation. And marginally, all of the potential predictors are positively correlated with distance. So this is going to be problematic, and we're just going to begin by estimating a model with only right leg and overall strength. So what we can see is that in both instances, they are positively associated with distance, as we may suspect, and that relationship is statistically differentiable from zero, indicated by our p-values that are below the critical threshold of 0.05. So this seems to be working in the way that we may expect, right? And we can see that our multiple r-squared value is quite high. So these two variables are explaining about 78% of the variation that we see in distance, which is a positive sign, right? That both predictors are significant and their coefficients are in the direction that we would expect. Now we're going to go ahead and include more predictors, many of which we know are strongly correlated with each other. So this time we're going to include hang time, left leg strength, right leg flexibility in addition to what we already had for right leg strength and overall strength. Now what we can see is that none of these predictors are differentiable from zero, which we know is not the case. That's also problematic, mostly because of the fact that we have induced more variability into our estimates, which has made our standard errors larger, which has the main reason why we cannot say that the betas are different from zero. Yet you'll notice that the R squared value is quite high. If we go back, we've now improved it to about 80% of the variation in distance is explained by our model. Now, the regression coefficient for hang is negative. We know that it is positively related with distance. So again, this is another signal that something wrong is going on. So what should we do? Well, let's go ahead and calculate our VIF in R. And we can do that by, again, running a regression with one variable in as the outcome and the others as the outcome, and checking the R squared value for each of our covariates. Now, if we do that, again, you can see we can do that by hand, which this would be where hang is our J variable, and then we calculate our VIF, which is 8, and we could do that for all of our variables. We could then do R strength as the outcome, and then hang would be a predictor, calculate it, and so forth. Or we can use this nice built-in function in R through the car library. And if we do VIF with a regression object that has all of our covariates in it, it's going to give us back the VIFs for all of the covariates. So again, we can see that hang has a VIF of approximately 8, while left leg strength has the largest VIF with approximately 9. This means that left leg strength is the variable that has most of its variation explained by the other covariates.